What is modeled simulation? A static model can be as simple as artificial skin and tubing for an IV or as complex as a computer simulation of the lung. Most patient simulators utilize a static model where modifying one input results in the change of one output. CAE utilizes a dynamic model, modeled simulation, where multiple inputs can be changed, resulting in multiple outputs, which more accurately mirrors human physiology. SISO, single input, single output. MIMO, multiple input, multiple output. William Van Meurs, co-inventor of CAE's products HPS and Muse, in his book Modeling and Simulation in Biomedical Engineering, stated, "Modeling and simulation are powerful ways of studying systems when direct interaction with actual system is limited or undesirable." Modeled physiology is represented in several CAE simulators. Different physiologic models are running and interacting with each other to produce a more lifelike response to treatment and procedures. The three primary models are cardiovascular, respirator, and fluid balance. We also utilize a pharmacological model to show the effects within modeled physiology. In the following video, you will observe how we have utilized the CAE Muse software to demonstrate physiologic modeling. The drug, succinylcholine, a neuromuscular blocker, will be administered to the patient. Notice how the respiratory rate initially increases with less volume, and then the patient stops breathing as full neuromuscular blockade is achieved in real time. Also note the pulse oximetry begins to decrease after the patient stops breathing. In the next video, you will see normal baseline physiology as represented by stable vital signs. Then, by choosing and adjusting respiratory parameters, symptoms of respiratory illnesses, such as pulmonary embolus, have been simulated. In this case, increasing the shunt fraction tells the body that the amount of oxygen level in the bloodstream has decreased and that the body is consuming oxygen at a higher rate. For more pronounced changes to vital signs, we can also increase the oxygen consumption rate. In the previous video, we changed the shunt fraction and oxygen consumption parameters with the physiologic model, which resulted in unstable vital signs, including decreased pulse oximetry, increased heart rate, and respiratory rate as expected. In this next example, you will see that if a static value or override for a vital sign is selected, changes made within the parameters now will not influence the overridden value. We will show you that by selecting a static vital sign, in this case the pulse oximeter, the software alerts you that an override has been chosen by highlighting the value in orange, and then regardless of other changes, this value will remain in effect. If the override is deselected, the value will then respond to the Physiology software as expected. Extreme changes in physiology may be challenging for the model. It may not encompass the entirety of all medical and physiologic processes. The modeling may not be inclusive of all medications or illnesses. Modeling does require more preparation and a clearer understanding of physiological processes on the part of the operator to improve comprehension. Modeling allows the educational experience to focus primarily on the learner by decreasing the amount of manipulation the operator must do for the simulated clinical experience. Modeling helps to ensure consistency and reliability in the simulation process. Modeling assists the healthcare educator to create a realistic patient experience for the learner. Using modeled software in the classroom can assist in demonstrating complex physiologic processes and responses. Allows students to experiment with potential treatments and interventions separate from the hands-on simulation experience. Enhances understanding of physiologic processes for all involved in the educational experience.